Assalamualaikum and good morning to everyone. Okay. My name is Rajiv Firansha bin Raja Ahmad Kasha. My matric card number are 01DEP23F1004 and my partner are Syazwin Laki Subramanium. The card matric are 01DEP23F1032 and we are going to present question 4 and our lecturer are Puan Hashamiza binti Harudin. Now we are going for introduction. The fifth generation mobile communication system incorporate advanced technology which include millimeter wave transmission, massive multiple input, multiple output, or we call it MIMO, and network densification to provide ultra high data rates, low latency, and to connect massive amounts of devices. A primary change in the architecture of 5G is the use of smaller cellular size with small cells, micro, pico, and femtocells used in conjunction with macro cells. The dense nature of the network allows for more efficient spectrum reuse, as the same frequency bands can be reused several times in very close proximity, it means less than a kilometer, of each other without significant interference. As a result, the base station and end user equipment can operate at lower transmit power, reducing the energy required per bit. Spectrum reuse using shorter cells size is the main contributing factor in improving overall energy efficiency of 5G networks and meeting global goals of sustainable and green communication systems. So now we are going for the questions. At 3.5 GHz in 5G mid-band, calculate the free space path loss at distance of 100 meter, 500 meter, and 1 kilometer. Then discuss how shorter cell size in 5G can save energy through efficient spectrum reuse, and use at least 5 journals to support your answer and present in YouTube. Okay, next. The free space path loss calculation. Okay, now for the solution. So we are given frequency 3.5 gigahertz and our distance are 100 meter, 500 meter, and 1 kilometer. So we are using formula FSPL in dB equals to 20 log 10 distance plus 20 log 10 frequency plus 23.44. Okay. So the distance we using in kilometer and the frequency we are using in megahertz. So we are going to change 3.5 gigahertz to megahertz. So we are times with 1000 and 100 meter and 500 meter we divide by 1000 to change the 1 kilometer to change in kilometer. So the first step, using the formula, so we insert the d and frequency into the formula, and for the first 0.1 kilometer we will get 83.32 decibel, and number 2 are 97.30 decibel, and the third 1 kilometer are 103.32 decibel.
The second question, discuss how shorter cell size in 5G can save energy through efficient spectrum. Firstly, in 5G network, the implementation of smaller cell size such as microcell, picocell, and femtocell plays as a crucial role in improving both energy efficiency and spectral utilization. The fundamental idea is that shorter transmission distance require significantly less power for communication, as demonstrated by the path loss calculations. According to Selimax, which is first journalist, reducing the distance between the base station and user equipment minimize interference and signal degradation, resulting in higher quality connections with lower power output. This contributes to reduce overall energy consumption at the network level. Moreover, cells enable spectrum reuse, which is major advantage in dense urban environments where user demand is high. Since each smaller cell cover only a limited geographical area, the same frequency band can be reused by multiple nearby cells without causing harmful interference. The second journalists say this lead to a higher spectral efficiency, allowing more users to be served simultaneously within a same bandwidth. As noted by Edgewell et al., which is second journalist, energy efficiency in 5G can be enhanced not only through hardware improvement but also by optimizing network architectures that minimize transmission losses. Research by Zhang, which is third journalist, highlights that reducing cell size directly impacts system capacity and energy savings. When a smaller cells are deployed, the power per unit area decreases while maintaining high data throughput. Additionally, many 5G base stations support adaptive power control and sleep modes, which allow components to deactivate when transfer is low, further reducing energy consumption. The UST report, which is fourth journalist, also emphasizes that small cell networks enable dynamic scaling, activating more cells only when needed, resulting in a more sustainable network operating model. Finally, as confirmed by studies from NCBI, which is a fifth journalist, small cells architecture not only reduce energy requirements but also support spectral and spatial efficiency through techniques such as beamforming and massive MIMO, which is multiple input, multiple output. These features concentrated the signal energy toward active users, reducing unnecessary power expenditures and interference.
And so for the reference, we're using five reference. Okay, the first one are CellMats, and then from NDPI, and then ResearchGate. For the fourth, we are using UST, and lastly NCBI. Okay,
In conclusion, the analysis of free space path loss FSPL at 3.5 GHz shows that signal attenuation increases significantly as distance grows, highlighting the importance of using shorter cell sizes in 5G networks. Smaller cells such as microcells and picocells minimize transmission distance, which reduce power requirement and improve energy efficiency. This approach ensures consistent signal strength, better coverage, and higher data throughput while maintaining lower overall energy consumption. Moreover, shorter cell size promote efficient spectrum reuse by allowing multiple cells to operate within a same frequency bandwidth, minimal interference. This not only enhances spectral efficiency and network capacity but also contributes to sustainable 5G operation. Through small cell deployment and adaptive power control, 5G network can achieve faster data transmission, reduce energy demand, and improve reliability, ultimately supporting the goal of creating greener and more efficient wireless communication systems. That's all for us. Thank you.